Hello everyone, I hope you're doing very well. Today we're going to talk about the next step in our CFD process, which is mesh generation. So going back to our CFD process again, last session we explained about geometry modeling, which was the first step. Now we want to talk about mesh generation, which is the second step for us. So the grid or mesh or SAL, collection of SAL, is being used in CFD, and we discussed this previously, but it is being used because of our basic assumption that we made when we were developing our Navier-Stokes equation, continuity equation, and the energy equation. And that assumption, if you recall, was that these equations are being developed on infinite small differential size control volumes. So when we are dealing with a big fluid system and we are solving our equations on it, first step would be to divide this big control volume to smaller pieces, smaller control volumes that are called cells, in order to make our equation development assumption correct. And these small control volumes are called cells, and this process is called meshing or mesh generation. So the importance of our grid is that basically it will determine your rate of convergence, your solution accuracy. Solution accuracy is obvious because as you make smaller cells, smaller and smaller, you are getting closer and closer to your mathematical assumption that your control volume is infinitely small. For that reason, you're reducing your error and make it more accurate. It also, remember that whatever we are solving on these control volumes, the equations are being solved numerically, and any numerical method involves an iterative process that you basically converge to that one accurate result. So mesh has a great effect on your rate of convergence, meaning whether it will converge or diverge, or if it is going to converge, what's the rate of convergence? Is it fast, slow, so on and so forth? Okay, it will impact your CPU time, and also it will impact your mesh independency. Meaning, if you have smaller cells, it's going to spend more CPU times, and if you have a complex mesh, it's going to spend more CPU time, so on and so forth. It will also impact your mesh independency, meaning that this is actually a new concept, meaning whatever mesh we create, any mesh that we generate on our geometry, that mesh has to be in a way that your solution is independent than mesh. Meaning, if I have a mesh and if I'm performing simulation, okay, and I will get some results, if I change the size of my mesh or the type of my mesh or the configuration of my mesh, my answers, my results should not be changed. Of course, it will change, but anytime, because you have different errors and so on and so forth. But the point is, it shouldn't change in any significant way. If your results are significantly changing by your basically mesh, it means your results are mesh dependent, and generally speaking, being mesh dependent is not desirable in CFD. So these were the effects, the importance, the reasons the grid is important. And these parameters will be determined using basically your mesh quality. So mesh quality is the parameter that defines your quality of your grid and the impacts that it will have on your simulation. These quality parameters are basically your grid density, number one, meaning how many cells you have in what area. Your cell lengths and volume ratios. So how are the lengths and volume ratios for your cells? The skewness of the cells. What type of cells you have, tetrahedral or hexahedral. Okay, your boundary layer mesh, and so on, so forth. So these will be items that we will be discussing today to see what we can recall a good mesh and how we can make them in our geometry. So there are many types of grids or mesh that are categorized in here, and you see them. The two main categories are structured and unstructured mesh, and underneath you have hexahedral or quad mesh, tetrahedral or tet mesh. So we will cover the first level and the second level. Anything beneath them would come as we start creating mesh. Okay, guys? So these are the important steps, important classes, the structured and unstructured, hex and trimesh. So that's why we will be covering those in our class. So first, let's start with different cell types, individual cell types. There are many different cell types, especially in 3D. So in 2D, the types are different. I think 3 or 4 different types. But in our class, since we are focusing on ANSYS, and as a matter of fact, this is not only ANSYS specific, this is correct for, generally speaking, major softwares. We have 2 basic cell types in 2D. One triangular and the other prism or 2D quadrilateral or quad. So we call tri and quad meshes. So in 2D, as far as we are concerned, we basically have 2 mesh type, the tri type and quad type. But once these 2 mesh type goes into 3D, depending how we make the volume in 3D, they would have different types. For example, from the base of tri, you will have tet mesh, which the base is tri. You can have pyramid, which the base is quad, and you can have arbitrary polyhedron. For 2D, you can have hexahedron and wedge type. But 99% of the time, the type of mesh that we will be working on would be tet and hex. So these 4 are our building blocks. In 2D, we have tri and quad. In 3D, we have tet and hex. So before moving on to generating our actual mesh, let's get out of the way some vocabularies. So you have your cell, which is your control volume. You have node, which is your grid point on here. So these are nodes, grid points, where the edges of a mesh cell meets each other. You have cell center, which are the computation node. If you remember from our numerical method session, that's basically where the calculation is being done. Then you have edges and faces and also the whole domain. So now that we have the vocabulary and we know about the different cell types, let's go to actually our different mesh grid types. So one of them, as we discussed, is structured grid. So in the structured grid is basically a single block structured grid, and all the grid lines must pass through all the domain and meet at the other end. So if you look at in here, every line starts at one boundary and it continuously goes and ends on the other side. So every single one of them is like that here also. So it doesn't need to be a straight line, just it needs to start in one boundary and end on the other boundary. So this is called a structured grid. But the problem with the structured grid, I mean, the advantage of a structured grid is very simple. It makes the simulation easier because the calculations on structured uniform shape units are much easier. You will have better convergence, more accurate results, so on and so forth. But the problem with it is structured grid cannot be applied to many systems because of the limitation it has, which is start from one end to another end. It worked for sure for simple geometries, specifically 2D geometries, and some, of course, 3D geometries. We will be using it in our class, but generally speaking, it is not very practical because once you move to complex geometries, you won't basically you won't be able to use this system. The next one is called unstructured. Generally speaking, unstructured does not have any specific rules. It is the cells are arranged in an arbitrary fashion beside each other. So you will see all the cells, different sizes, different types, arranged beside each other. This is called unstructured. This is most useful, not very easy to simulate, but the good thing is it can be adapted almost to any sort of geometry. More desired type of mesh, which is not a new type, is a hybrid of two, which will combine the accuracy of a structured grid with the flexibility of unstructured. It's called hybrid grid. So in hybrid grid, what you do is wherever you can, you use structured, and wherever you can't or you don't care, you use unstructured. Here, for example, is a very good example of it. It is a cross-section of a wing of an airplane, which is called airfoil. So if you cut the airplane wing and look at it in a normal direction, this is what you will see. And we want to see how the flow around this airfoil works. So for that reason, we put structured grid near the airfoil, because as you can imagine, as we get closer to the airfoil, it becomes more and more important, and it becomes more critical to have more accurate result. And you see this black thick line in here. Actually, if we zoom in, you will see, if I'm correct, 50 or 60 different layers of cells in here. So it's a very refined, correct mesh. But as you get further away from your airfoil, the simulation becomes less important, because you're not interested in those parts and you're very interested in near the airfoil. For that reason, for the simplicity and for the sake of using less cells, you use unstructured. Because guys, remember, our rule of thumb was that simplify your simulation. One big step of simplifying the simulation is in mesh generation. Try to make as much as possible less number of cells, because if you increase the number of cells, essentially you are making your simulation more difficult. So now let's look at some guidelines, some general guidelines on how we can make a better mesh and what would be considered a better mesh. So number one is, when you're making a mesh, you have to make the mesh in a way that it resolves all the flow features. For example, in here, you see here is the flat plate and the flow near the flat plate, which goes to 0 as we get closer to the wall, right? So if you want to simulate this and capture proper change of velocity, right? And remember, velocity is only being calculated at the cell centers, right? So if I put only 3 layers in here, so I won't see the change very, very properly. Or even worse, if I put 1 cell in here, I won't see the change in velocity from 0 to whatever it is at all, right? So by resolving flow feature means put enough cells, or in other words, put enough calculation points in there, computation nodes in there, to be able to see that feature clearly. So this is number 1 rule, okay guys? So number 1 rule is that you will perform mesh generation in a way that you have enough data in areas that matter. So if you have a change in pressure, change in velocity, change in temperature, generally speaking, a gradient means change, a gradient of a parameter at any direction, make sure you have enough cells in that direction. Okay, so the next guideline is regarding to grid independency. Remember, we talked about being mesh dependent. This is that point. So one thing you have to consider about, we have to be careful, is grid independency. You cannot achieve grid independency in all simulations, and it's not very important in many simulations, but if you can get closer and closer to grid independency, that would be great. Here you see the general concept of it. The green line is your real answer, real world physical answer to your solution, and it is constant, right? Because it doesn't recognize your mesh. It's not mesh dependent. It's just one physical answer, one velocity, one pressure, so on and so forth, right? The red line is your simulation. So as you increase the mesh resolution, okay, as you increase the mesh resolution, you are increasing the accuracy, getting closer to the real answer. Okay, so remember, since we are getting closer to the real answer, we are getting closer to our grid independency. So higher resolution means more accurate result and better grid independency. Okay, so being accurate is one of your goals, obviously, right? So getting closer to the real answer by increasing the mesh resolution, meaning increasing number of cells or making cells smaller, would basically get you closer to the real answer, which the immediate effect of it is more accurate result and grid independency. But the trade-off is higher the resolution, longer the simulation. And you remember, this is against our general rule of thumb, which was basically simplify your simulation, right? For that reason, this is a trade-off. And you have to make the results, the resolution in a way that the results are accurate enough. Remember, that's very important, accurate enough, but still you have not very large simulation. For example, if this resolution is good enough, don't go for this. Okay, don't make it unnecessarily more refined to get unnecessary accurate result. What would be a definition of good enough? That's a subject by itself. It basically involves what are the phenomena, physical phenomena in your system, what is important for you in that simulation, what are you trying to analyze, and so on, so forth. So the grid independency, here is another example. You see, this is the number of grids, and this is, for example, maximum concentration. This is a simulation inside the pipe. You would calculate the maximum concentration of a material at some point. You see, as I increase the number of cells, my concentration changes, meaning my results are grid dependent, which is wrong, right? By changing the resolution, it shouldn't change the concentration. So what I would do is I keep increasing my grid number of cells until I get such sort of graph. Meaning, you see, after a while, by changing the number of cells, the results almost stays the same. And this would be the grid I will be using, the number of grids. Why? Because at this point, this is the least number of cells that I can use to achieve grid independency. I won't use this because, true, this is grid independent too, but it goes against my rule of thumb, which is simplify the equation as much as possible. So this would be the minimum number of cells that still I will get grid independency with lesser number of cells. So other guideline is smoothness, meaning if you are creating mesh in your system and basically due to many considerations of the flow features, so on and so forth, you need to refine or coarsen your mesh from one step to another one, right? A smoothness means the size of the neighboring cells should not be different dramatically. For example, two neighboring cells, one shouldn't be 100 times larger than the other one. If you want to go from size of 1 to 100, don't go in one step. You have to create different steps, go from 1 to 2 to 5 to 10, so on and so forth, until you reach to 100, right? So that's the smoothness. The general rule of thumb is that your neighboring cell, if it is supposed to be larger than this the other cell, shouldn't be 20% more larger. So delta xi plus 1 should not be divided by delta x, should not be less than 1.2. Is this some rule written on stone? No. You would come across many examples that this 20% would have been increased to 100%, 80%. But the point is, whatever rule we put in here, the smoothness, the other rules, has to be applied to the majority of the cells. Can it be applied to all the cells? Well, if you can, that's ideal situation, but practically, no, you can't. You only can apply those rules to 80%, 90%, 70% of the cells, and that's good enough. So the other thing is aspect ratio. So in aspect ratio part, basically what happens is very similar to smoothness. In here, for example, the aspect ratio of this is 1 because the length divided by width is 1. So, and this is a very high aspect ratio cell. So remember, using a very high aspect ratio is undesirable. Using some sort of more than one aspect ratio is sometimes actually desirable because it will decrease the number of cells in a direction that is not important, and it will increase a number of cells in a direction that is important. For example, you see this one. If for some reason I have a change of velocity in this direction, in vertical direction, but not in horizontal direction, this would be kind of ideal cell for me, because if I put all the layers on top of each other, in vertical direction I will have refined cells, and in horizontal direction coarse mesh, which is best case scenario for us. But having said that, the aspect ratio shouldn't be 10, 20, so it has to be something beneath 10 ideally. The other thing is skewness. Skewness basically is the definition of how distorted the cell is, and the way you do that, you will compare the size of your cell to the size of an equilateral cell. So that would give you, or the angles of your rectangle to a perfect square. Okay, so these will give you some sort of sense, okay, how distorted my cell would be in the system. What are the numbers, acceptable numbers for skewness? We will see in a moment. So the other guideline is the total number of cells. So basically in here, what will happen is, remember, keep the cell count down. Okay, don't use more than necessary number of cells. Okay, guys, have that in mind. And generally speaking, in CFD, if you have 10,000 more, it's generally considered small problem. 100,000 more intermediate, 1 million or more large, and 10 million more are huge problems. These are all relative. They're not written in stone, but this is what's being used basically in common CFD simulations. So the other concept that before actually moving to mesh generation is grid adaptation. So grid adaptation goes back to that concept of hybrid grids. So, and having simplified problems. In grid adaptation, what happens is basically you want to, the idea is you want to make the grid small, refined, wherever you have a gradient, wherever you have a big change in your parameter, and make it a coarse mesh wherever there is no much of a change, because you want to decrease the number of cells. That's where this grid adaptation philosophy comes from. So in some problems, it's easy. You know the velocity is changing near the wall, and that's true throughout the simulation. So you make this mesh near the wall very refined. But sometimes it's not as easy as that. Sometimes what happens is your gradient moves inside your domain. So you know you're going to have some sort of velocity or pressure gradient, but you don't know where exactly. For example, on an airfoil in here, or a better example in here, you have a bullet that is moving in the air. Because of the high velocity of the bullet, what happens is you will have compressed air just at the tip of the bullet, which means you will have a very large pressure gradient at this area. But the problem is your bullet is moving. So what are your options? Either make the whole thing very refined to capture that gradient everywhere, but you will probably end up with 100, 200 million cells. Or the other option is, no, I will refine my cells wherever that gradient exists, and once that gradient passes through, I will coarsen my mesh. That's a gradient adaptation. You see in here, as the bullet moves, the line in front of it becomes refined, and as it passes through, it again goes back to coarse. This is called gradient adaptation, and this is being done in the software automatically, of course, using the controls that you have given the software. We will see the example if we come across in our workshop. So now let's move on to mesh generation, and these are ANSYS specific functions that we will be using to generate our mesh. So in mesh generation, also same as geometry modeling, we basically have 2D meshing and 3D meshing. In 2D meshing, we have 4 automatic type of method. We have the automatic, triangle, uniform quad tri, and uniform quad. And you basically see the difference. In automatic, software will take some general settings, which we will come back to those general settings. The general settings are called global settings. So the software will take those global settings and create a mesh, and wherever it suits, it will use whatever it sees fit. In triangle, what will happen is it will only use triangular cells. In uniform quad, it will use uniform quad, it will use only quad cells, and in uniform quad tri, it will use a mixture of those cells. So in 3D meshing, we will have basically 6 different methods for meshing, and which in this class we only will cover the first 4, the tetrahedrons, hex meshing, sweep meshing, and automatic. The last 2 is not introductory, and it has a specific application. So let's see what these meshings are. So in tetrahedrons, which is a patch conforming meshing, what will happen is every solid is simple, like a triangular solid. Everything is meshed with tet meshes, okay? But only thing is, it would be patch conforming. In CFD, we always use tetrahedron patch conforming. You see the difference. If you have 3 circles in here, in patch conforming, the mesh will adhere to those circles. Whereas in patch independent, you won't see those circles. And for us in CFD, always and always, we use patch conforming. You have hexahedral meshing, same as tetra. The only thing is, based on your global settings, it will create mesh with only quad cells. And one big advantage of using quad mesh to tetrahesh is you will end up with much less number of cells. And you see here the example. In tet mesh, for the same for this geometry, you have 48,000, whereas the similar quad mesh are only 19,000 cells. The next method is sweep meshing. So sweep meshing usually is being used for a geometry that is the cross section does not change in the length, usually an extrusion. You see here. So the idea is, if I have this geometry where wherever I do the cross section cut, I will see essentially this face. So in sweep meshing, what you do is you mesh the face at one end, then start copying that mesh in predefined distances. So this will ensure wherever you cut, you will see that mesh that you have created. For that, you have your source mesh, the destination source face, destination face, and the sweep pass. So basically, when you're using sweep, you mesh one face, then go to the sweep options, and you give it, you determine the source face, the target face, and also the distances between the copy-paste surfaces. So, and it will create the mesh throughout the geometry for you. The last method is automatic method. In automatic method, as I said, software will take your global settings, which is, we will come back to this, and based on those settings, which are very general settings, it will create mesh throughout your geometry. Now, what are the global mesh settings? They are being called global as opposed to local settings. So global settings are the set of options that are being applied everywhere inside your domain. Local settings are the settings that are being applied to specific locations, specific surfaces, specific volumes that you determine them. But the point is, local settings always precedes global settings. So wherever you have you enforce local settings, in those specific areas, your local settings will overwrite your global settings. The point is, you can start meshing using global setting everywhere, and then modify your mesh using local settings in different locations. And these settings, these controls, are many things from sizing, inflation, patch conforming option, defeaturing, so on and so forth, which we'll be covering some of them in here. So one is called relevance. So basically, relevance is a qualitative, parameter to see how refined or coarse your mesh is. Your relevance changes in three categories: fine, medium, and coarse, which minus 100 coarse is the coarsest, and plus 100 fine is the finest. So it's a kind of a qualitative way of instructing software how refined or coarse you want your mesh. The other one is advanced size functioning. Basically, in advanced size functioning, you will instruct the software what to do near specific features. For example, refine the mesh around the circles, around the holes, or refine the mesh when the cross-section changes. General instructions regarding different things that you see in the geometry. Then you can define element size. Okay, so you will say to the software, what would be the minimum element size that you are allowed to use in meshing the whole geometry? What would the maximum face size for a 2D or 3D mesh? Or what would be the maximum volume size for a three-dimensional mesh? So these three numbers basically will put a clear guideline for the software that in what range of numbers, what range of sizes it can generate mesh, both in 2D and 3D. Then you have the sizing or growth rate. So you can, you remember I told you, if you're going from fine to coarse or coarse to fine mesh, you have to be very subtle, you have to be smooth, you can't jump from very coarse to very fine, so on and so forth. This is the parameter controlling that, growth rate. So basically, how you want to grow, enlarge your cells from one cell to another one. And you see this has a great effect. For example, with 1.1, the number of cells would be more than 1 million in this example. But if you make this 1.3, meaning your speed up your change, it will go less than 400,000. So this is a number that will have a great effect on the number of cells that you are having. Then you have the transition. This is also a qualitative manner similar to growth rate, but it's very qualitative, which you have the option of fast and slow, which will tell the software how fast or slow it has to move from one size mesh to another one. Then you have a smoothing. In a smoothing, what happens is basically this is being applied after the mesh is complete. And in smoothing, the software, you have three options: low, medium, and high. And what happens is usually after it's being applied after the meshing is complete, the software will go through all the mesh and will try to smooth it up. So get rid of the weird shaped cells, make the cells more smooth, the changes are smooth, so on and so forth. This is basically a final touch on your mesh generation process. Then you have something called span angle. So basically, span angle, what happens is it will tell the software you have three options again: coarse, medium, and fine. And as you see the example in the picture, it's very clear, right? How refined you want at sharp edges and sharp points. Then you have the inflation. Inflation option is usually used for boundary layers. You will see in our example next session. So it's being used for boundary layers. So it will give you ultimate control, especially near the walls, that how many layers with what resolution you want to put close to the wall. So that's inflation is basically used exclusively for near the wall flows and resolving boundary layers. Now, the local mesh controls, as we mentioned, they are very similar to general global cell controls. The only difference is they overwrite your global cell controls. Now, in every mesh generation process, after we complete the generation of our mesh, what we will do is we will go and check our mesh and looking for errors. Basically, the errors could be that mesh is too coarse, the skewness are high, large jumps in volumes, large aspect ratios, and negative volume mesh is also very important. Okay, so these are the errors. The way we detect the errors is through the mesh quality matrix. So in mesh quality matrix, what we'll do, you will have some parameters. By checking the value of those parameters, you basically determine how good or bad or average your mesh is. The most important ones are the aspect ratio, smoothness, and skewness. So, for example, for skewness, in your mesh control, mesh quality control panel, which we will show you in a minute, you will go and check for the skewness. The matrix for being good or bad is shown here. So anything below 0.8, a skewness of 0.8 is acceptable. Anything above that, up to 0.95 is poor. You can continue with your meshing, with your simulation, but it's not desirable. Anything beyond that, you have to go back to your mesh generation and correct that. And the point is, guys, usually speaking, when you analyze this on this or aspect ratio on your system, you probably will end up having different number of cells in each category. Of course, not degenerate or silver. The point is, you can make every single cell excellent, and not every single cell of your mesh would be poor. The point is the majority of the cells. Where are the majority of the cells? As long as the majority of cells in the good or acceptable portions, you're good to go. And majority means more than 90%. Okay? And always remember, you will have some cells that are undesirable, they are poor in quality, so on and so forth. Although it's very good to correct them, but you cannot be successful in doing that every single time. This is the mesh matrix graph, which you see here. Basically, as you see here, for example, it is one of the parameters. I'm not sure which one right now, but it gives different numbers for you and the number of each cells in that direction, in that category. And if you highlight every single one of them, it will show you those cells. So this is very good because if you have poor cells, you can highlight them and see where the problem is and try to fix it, basically. So before we wrap up, the last part in our mesh generation is something called name selections part. So once you create your mesh, so you have your geometry, you have your mesh, now is the last step, and what the last step is to basically import this to your simulation software, right? So to import them to your simulation software, what will happen is basically you need to define your boundary conditions in mesh application. Okay, by defining your boundary condition means define where are the geometries and assign names to those geometries. These are called name selections. So basically, name selection, what you would do is, for example, for your velocity inlet or velocity outlet or walls, you will select that surface and name that surface. Once you do that, when you import your mesh and geometry to your simulation software, it will automatically assign boundary conditions to those surfaces. When you are naming it, there's a code for it. When you are naming it, remember guys, your first word is important. For example, if you want to use inlet, just name it inlet something. It could be inlet your own name, but the first word is inlet. If it is inlet or outlet or pressure inlet, the simulation software will automatically detect that and assign proper boundary condition to that. What happens if you do it wrongly? Oh, nothing big will happen. In simulation software, you can always change the type of boundary condition, but it's always better to organize everything here in meshing. Okay, guys, this was the subject of meshing. And next session we will go actually into our simulation software and we will start simulating. Thank you very much.